Hello, let's talk about manipulated Jacobian. Particularly, we'll talk about where it comes from, how is it used, and what does it mean. There are also some really nice treatments of how it is derived in various textbooks. We will not be covering that, but I may make a remark on that. But first, let's get started with what is a Jacobian. So, in robotics language, you would say Jacobian. Jacobian means manipulated Jacobian. The very simple idea behind it is you typically, if you take an example like this, which is a two-link robot with two links, you typically are able to control what is happening at the two joints because the motors are things you can directly control, and it is also typically easier to measure what is happening at the joints. So you know the angular velocity of the first joint, let's say q1 dot, and you know the angular velocity of the second joint, q2 dot. But what is of interest to you as a roboticist is what is the robot end tip doing or the end effector doing, and let's call that point P. So what is the velocity of point P? You want to know that, but you can only measure these. So Jacobian is nothing but the relationship between these two things that you can measure and what is happening at the end. So in terms of equation, you would have velocity is equal to a matrix, which is the Jacobian, times q dot, and here there are a few comments in order here. When I write q dot, it's now a vector, and the first component of vector is q1 dot, second component is q2 dot, so it's a two-dimensional vector in this particular example. And the velocity here, if we assume everything here is planar, so the robot is just moving in the plane, so the velocity will have two components again because x and y components, right? So this is also a two-dimensional vector. So this Jacobian then becomes really a matrix, and in this particular example, it's a 2 by 2 matrix that relates what is happening, the velocities or more specifically angular velocities at the joints to the end effector velocities. Now we will add a few more details here. One, let me write this as Vp because it is the velocity of point P, so we are clear what we are talking about. And this J, let me add a subscript of V. The reason being, there is also a more general form of Jacobian, which is when you're relating the joint angular velocities with not only the end tip velocity, but also the angular velocity of the end effector frame. Right? In this case, this J is a slightly, it's a different J. It consists of J, V, and J omega. And sometimes when people say Jacobian, they usually mean this whole matrix. And this is just the velocity part of the Jacobian. But anyway, we will not get into that for the moment because the ideas that we will discuss here are exactly applicable over there as well. And usually from the context, it is clear whether people are talking about this whole Jacobian or just the velocity part. Okay, going back. So Jacobian is a matrix. So JV is a matrix. But there are a few things going on over here. One, the size of the matrix. In this case, it so happened in our example here, it so happened that it was a square 2 by 2 matrix. But in general, this is not square. Right? And it would depend on how many joints or how many degrees of freedom the robot has. And the velocity will typically be either two components, or if you're talking about motion in 3 dimensions, 3 components. So that will not depend on the number of degrees of freedom. Right? So in the general case, this is a matrix which is 3 by n. 3 because you're talking about 3-dimensional motion. So you will have 3 rows for this matrix. And n because you have n degrees of freedom, so you will have n components of angular velocities. Okay. So this is one thing to note. And if if you happen to be working with robots, the ABsix robotics robot, then that has 3 degrees of freedom. So in that case, again, you will get 3 by 3, right? If you're talking about 3-dimensional velocity. Okay. Now, couple of more things. While this is a matrix and it has real values, it is not a constant matrix and it depends on the configuration. So Jacobian is configuration dependent. What does that mean? It means that if the robot happened to be in a different configuration, so different joint angles, then this matrix will be different. It's still having the same size, but the values in it will be different. And to just visualize that, let's look at an even simpler example of a one-link robot. This is something that everybody is familiar with. It's just one link rotating at an angular velocity of, let's say, q1 dot. So one joint, angular velocity q1 dot, and then the velocity of the end tip is v. And then we have studied this in 10th, 11th, 12th, so we know the velocity v is nothing but q dot times this length l, and it will be tangential to this link, right? But if I think about its x and y components, then I would typically get, so if I simply write vx, vy, for this particular example, this is only for this example, this would be, I would get L q1 dot as the velocity, but the component of that along x direction will be the negative sine theta of that, right? So I would get a minus L sine, and in this case, theta meaning q1, sine q1 times q1 dot. And if I think about the y component, it would be the cosine theta. So I would, and it would be positive. So I would get a L cosine q1 times q1 dot. So in this particular example, so if I can just erase this a little bit just to avoid confusion, the matrix JV is 2 by 1 and it has the sine and cosine functions. But as you can see, it depends on q1. So if q1 is different, the numbers would change. So simple example would be when q1 is 0, sine of q1 will be 0 and this will be 1. So I get a 0 and L. But when q1 is 90, then I would get a 0 and minus L. So the matrix will keep changing depending on the configuration. So that is something to keep in mind. So this is configuration dependent. Okay. So it relates these velocities, but you can now start to see that it is useful beyond just the relationship between the velocities, because first it helps you relate what's happening at joints and end effector. Second, once you start thinking about the dynamics of the robot, you want to compute things like the kinetic energy, for instance, then you need velocity, and for that again you would use Jacobian. So in dynamics, you would see again Jacobian plays a role once you start deriving equations of motion. In the derivations, you would often use Jacobian. The other place you would use quite often is analysis of what is happening in the robot, or what are the robot's capabilities in different configurations. Just like we said here, right, that for a certain angle it is 0 and L, for another angle it is minus L and 0. It helps us see right away that for a certain angle you cannot get y component velocity at all, because this was 0. For a different angle, the first component was 0, and therefore you cannot get any x velocity. So it's an analysis tool that helps you analyze what are the capabilities of the robot in that particular configuration. So that's another place Jacobian is used quite a bit. And related to that is this concept of singularities. So what are singularities? Singularities are configurations in which the rank of the Jacobian drops. So it is not full rank. Now what would that mean? It would mean that at those configurations, either some components of velocities are not achievable. So you may not be able to get a certain direction of velocity, or it could also mean that to achieve certain velocities, you need infinitely large angular velocities, which means it is impractical. You cannot achieve those, right? So singularities gives you an idea of certain configurations in which the velocities are limited, right? And consequently, the capabilities of the robot is limited in certain directions. So that's again a very useful analysis that one could do with the Jacobian. There are two more things where you would find, of course, there are other aspects also, but the two more major aspects of robotics where you would find Jacobian feature quite prominently. One of those is force statics. So that would be a situation in which, let's say, the robot is pressing against an external object. So there is a force applied by the robot on the object, or some aspect of the environment. Maybe it's a table, maybe it's a wall. The robot is pressing against a wall, let's say. Then the force F that the robot is applying on the wall, again, let's imagine that that's not directly measured, but you can measure the torques at the joint. So you have tau 1 and tau 2. So again, you would have a relationship between force applied by the robot on the external environment and the torques applied by the motor at the joints. And a very simple way to derive this relationship is to just say input power to the robot is the same as the output power, assuming no losses. So the input power would be tau transpose q dot, and the output power would be F transpose V. So work done is force times distance, and power is rate of change of that. So force times velocity, but writing in vector form, you write F transpose V and tau transpose q dot. And you can see right away that I can now, this would be Vp. I can use this relationship here. I can substitute that here, and I would get F transpose JV q dot is equal to tau transpose q dot. So from here we can conclude, so I'm just equating these two, and then I will just transpose them for convenience. So I can figure out that I get tau is equal to JV transpose F. So what this equation tells me is, to be able to apply a certain force F, the torque that I need to command at the joints has to be JV transpose F. So again, Jacobian plays a prominent role here. Jacobian relates what torques I need to apply at the joint to get a net effective force at the end effector, at the end. Okay, so this is force statics. Now, one last aspect that we will cover today in terms of Jacobian is the role of Jacobian in inverse kinematics. So just to recap very quickly, forward kinematics is when you know all the joint angles and you want to find the end effector coordinates, right? That is forward kinematics, and that is typically some trigonometric relationship, so it's easy to compute. But inverse kinematics is harder to compute because you are solving for the joint angles, and this is still velocity relationship, but you can imagine you will get sines and cosines. Now when you have let's say something that looks like x is equal to L1 sine q1 times cosine q2 and y is equal to some other combination of these trigonometric functions, then solving for these variables are harder, and it gets progressively harder when you're talking about multiple degrees of freedom. When you have 3 degrees of freedom, 4, 5, 6, this becomes impossible to solve by hand or solve in closed form. So there are a lot of these iterative methods for inverse kinematics. So bottom line, inverse kinematics is harder, as you might have already been aware, and you typically try to use iterative methods to solve this. And one simple iterative method, now I'm just explaining the concept here, the way it is implemented is a little bit more sophisticated than that, than what I'm explaining here, but still. So one way to do inverse kinematics is, supposing we take the same equation that we had here, Vp is equal to Jv q dot, and remember, inverse kinematics means we want end effector position and want to figure out what we need to do the joints to reach that end effector position. You can think of this Vp, and this is an approximation obviously, as, let's say, position at, let me take another pen, position at the current time plus delta t minus position at current time divided by delta t. As you may remember, the limit of this as delta t tends to 0 is literally the definition of derivative of p, which is just Vp, right? So this is an approximation, and it is quite close to Vp when delta t is small, and we say this is still equal to Jv times q dot. Right? Now, if I do a little bit of jugglery here and I say this is my current position and my desired position where I want to reach, right? And let's assume that I want to reach there in one time step, although that's a big assumption. Now, if I say P desired minus current P and 1 by delta T, let me just call that some constant for the moment, K is equal to Jv times q dot, then this gives me an easy way. If I just move things around, I will write q dot is equal to Jv inverse times K times P desired minus the actual current position. Now, these are end effector positions, P, right? Position coordinates. Now, this gives me a simple approach to figure out how I should move the joint. So, q dot tells me how much I should rotate the motors or the velocity, angular velocity commands at the joints to help my end effector reach my desired end effector. Now, there are lots of challenges here. This is a very simple explanation of how it is typically done. One, this is an approximation. Two, you don't typically want to reach your desired position in one step, especially if you are far away. So, there's a lot more going on. Three, along the way, you may encounter singularities. So, your Jacobian may be losing rank. So, you do a little different approach. You do a, instead of doing a JV inverse, you factor in some additional aspects for addressing singularities. We don't need to get into that, but just giving you an idea. And last, we did say that Jacobian is not necessarily a square matrix. So you cannot directly take an inverse in most cases. So you end up taking a generalized inverse. But the whole point here is not getting the equation right, but getting the concept that you can use Jacobian and some form of inverse of Jacobian to figure out how to move the joints so that your end effector reaches a certain desired position. So this is a indirect way of doing inverse kinematics in an iterative way, but this approach is widely used with a little bit of sophistication added. So with that, we have seen quite a few different places in which Jacobian is used, relationship between joint velocity and end effector velocity. We've seen that it's a matrix that is configuration dependent. It can be used to analyze various things, including seeing where are the singularities. It plays a prominent role in force statics, and it is also used in inverse kinematics algorithms. The derivation of Jacobian is another story. We will not cover that here. But there are, based on the DH system, there are standard ways to derive Jacobians for any robot as long as they can be described within the DH system. And there are some good derivations explained in various sources. And there are also subroutines you can find directly to do that because it is so standardized once you start with the DH system. But that is not the point of this discussion, and that I would leave for a separate discussion.